Hello, my name is Mike Buller, and this video explores some of the fundamental principles relating to structural analysis and design. This video will consider a simply supported beam with a cantilever both to the left and the right, and demonstrate how to calculate the shear force and bending moments associated with the imposed load. It will also demonstrate how to draw the associated shear force and bending moment diagrams. As with any simply supported beam, the first step is to produce the free body diagram. And as you can see, the beam illustrated has a pin to one end and a roller to the other end. So to the pin there are two unknowns, to the roller there is a single unknown. That means the beam is statically determinate, and we can calculate the vertical reactions using our three equations of equilibrium. They state that the sum of the vertical forces equals 0, the sum of the horizontal forces equals 0, and the sum of the moments equals 0. We can see that there are no horizontal forces applied to this particular beam, so therefore we can simply write that HA, that's the horizontal reaction at A, equals 0. For the vertical forces, we can write that VA plus VB minus the sum of the UD loads minus the sum of the point loads equals 0. And then, considering our last equation of equilibrium, we can state that the sum of the moments at either A or B equals 0. So if we consider the sum of the moments at A equals 0, and we can then go on and take moments about A, equate that to 0, and that will give us value for the vertical reaction at B. For the sum of the moments at A equals 0, we are going to consider everything in a clockwise direction to be positive. And if we look firstly at the 12 kilonewtons per meter UD load, we have the vertical reaction at A, and to the left of it we have a short length of beam with a UD load acting in an anti-clockwise direction. So for the first part of it, we can say that minus 12 times 1.8, that's the load, times the length of beam over which it acts, times 0.9, that's the lever arm, plus, now the next part is positive because we're now considering the UD load acting to the right of the beam, and we have two of those. So we've got the 12 kilonewtons per meter and the 8 kilonewtons per meter. Both of those act in a clockwise direction, so they are going to be considered as being positive. So we've got plus 12 times 2.2, and again that's the magnitude of the load times the distance over which it acts times its lever arm, 1.1. Then we can consider the second UD load, so again it's positive, so it's plus 8 times 4.2, again that's the magnitude of the load times the distance over which it acts times its lever arm, that's 4.3 meters. So that's taken care of all our UD loads. Next we could consider the 25 kilonewton load. Again, that is acting in a positive direction, so it's acting clockwise. So it's plus 25 times its lever arm, 4.6. And the last load to consider is the 18 kilonewton point load to the end of the right hand cantilever. Again, that is clockwise, so it's going to be plus 18 times its lever arm, 10.15. So that's all the loads taken care of, and the last action is going to be the action at B. That is acting in an anti-clockwise direction about A, so that becomes minus 6.4 VB, and then obviously that all equates to 0 because the sum of the moments about A equate to 0. So we set that equation to 0, and from there you can simplify it, and we get 451.78 minus 6.4 VB equals 0. And then if we solve that for VB equals 70.6 kilonewtons. So that gives our vertical reaction at B. If we now go back to our original expression for the sum of the vertical actions, we have VA plus VB minus the sum of the UD loads minus the sum of the point loads equals 0. We want to calculate VA, so we have VA plus 70.6 minus the sum of the UD loads, so we've got minus 12 times 4, that's the 12 kilonewton per meter load, minus 8 times 4.2, and then minus the 2 point loads, 25 plus 18. And again that equals 0, and if we simplify that we end up with VA equals 54 kilonewtons. That's the first part of this problem. We obviously need to complete this before we can construct the shear force diagram. So that's the next step, is to construct our shear force diagram. So if we start by adding a simple line to denote the beam, and that is effectively going to be our 0 shear force. And then to that, it's simply a case of following the load, so following the direction of the arrows that we've already drawn for our load diagram and our free body diagram. So firstly, the UD load to the left of the pin support, we are going to lose 12 kilonewtons per meter over the first 1.8 meters. So starting at 0, we're going to lose 12 kilonewtons per meter over the first 1.8 meters. That gives us a value of 21.6 kilonewtons. From there, we now consider the vertical reaction at A, and that acts straight up and has a magnitude of 54 kilonewtons. So from there we draw straight up and we go up 54 kilonewtons. That gives us a value at that point of 32.4 kilonewtons. So we've got 32.4 at that point. We now consider the remainder of the 12 kilonewton UD load. This is losing 12 kilonewtons per meter over 2.2 meters. So if we plot that, that will give a value of a shear force at the end of the UD load of 6 kilonewtons. Now if we consider the first portion of the 8 kilonewton per meter load, so that's up to the 25 kilonewton point load, we're going to lose 8 kilonewtons over that first 2.4 meters. That's going to give a value of 13.2, so that's 13.2 kilonewtons. Now we have the vertical action associated with the point load, and that is going to lose 25 kilonewtons straight down. So that gives us a value of 38.2. And we can now consider the second part of the 8 kilonewton UD load. So that's losing 8 kilonewtons over 1.8 meters. That gives us a value of 52.6 kilonewtons. And the next one, we look at the vertical load associated with the reaction at B, and that is 70.6 kilonewtons acting straight up. So 70.6 acting vertically takes us up to 18 kilonewtons. Between the reaction at B and the end of the cantilever, there are no other loads acting, so therefore the shear force remains constant. So it remains constant to the end of the beam, that is 18 kilonewtons at that point. Now we have the vertical load acting down at 18 kilonewtons, and that closes off our shear force diagram. So we start at 0 and we end at 0. You should know by now that there is a relationship between the position of minimum shear and the position of the maximum bending moment in a beam. So where you have a 0 shear force on a beam, you will have a point where the bending moment is maximized. So for example, at this point here, we have 0 shear. So when we plot our bending moment diagram, we would expect to see a maximum moment occur at that point. So we need to calculate exactly where that point is. And if we look at the shear force diagram, this section of the shear force diagram is all linear. So the change in shear force is linear. So we have a triangular relationship. And if we just draw that as two triangles, we have firstly our main triangle, and inside that we'll have a smaller one. So we have similar triangles. If we add our two shear forces, our known shear forces together, at this point we have 6 plus 13.2, that equals 19.2 kilonewtons. And at this point we have 6 kilonewtons. So those are our two known shears that we've calculated previously. And we know some of these distances. The distance we're looking for is this distance x here. So that is x, because we know the distance from the reaction to that point, because the point here, this point here, at the end of where the 6 kilonewtons of shear is, that is the end of the UD load. So we know that point. We're trying to calculate x. We know this point here. We also know where 13.2 kilonewtons is, because that is the end of the UD load. So we know that distance. So that distance is a known, that distance is a known. And that one there, that's 2.4 meters. If you have a look back at the diagram, you'll see that. Let's just scroll up. We know that distance is the distance here. It's the distance from the end of one UD load to the point load. And the point load is positioned at this point is where we've got a vertical change in the shear force. So we know that distance, that's 2.4, so that there is 2.4 meters. And what we're after is this distance in here, and that is x. So we can write the relationship as 2.4 over 19 equals x over 6. As I say, simply a case of solving similar triangles. That gives you a dimension for x equals 0.76 meters. And if we write that in terms of a dimension from the support at A, let's call this dimension here Lx, we end up with Lx equals 2.2 plus 0.76, which is 2.96 meters. So that is the point on the beam where we have zero shear, and because of the relationship, where you have zero shear, you have a maximum bending moment. So at 2.96 meters, the bending moment will be at a maximum. Right, in calculating the bending moment at any particular point along the beam, what you need to remember is that for a simply supported beam, any load applied to a beam that gives a sagging of the beam, so the beam deflects down, the bottom is in tension, any load that gives that is positive bending. So a load on a beam that causes tension in the bottom of the beam, that is positive bending. And conversely, a load on a beam, so again we have a beam simply supported, load on the beam, the load is acting up, it is causing the beam to bend in the opposite direction. We will have tension on the top, that is negative bending. So positive bending will give a sagging moment, and negative bending will give a hogging moment. So you need to remember both of those as we go forward and calculate the bending moment. So you can consider each load individually, not all together, each load individually, and think whether that is causing a sagging moment or a hogging moment. If it's causing a sagging moment, it's positive bending. If it's causing a hogging moment, it's negative bending. Okay, so what we want to consider is the bending moments at A, C, D, E, B and F. So that's the various points along the beam, either where the vertical actions appear or where you have a change in the load. So starting at C, we know that the bending moment at a free end of a cantilever equals 0. So we can simply write the bending moment at C equals 0. And similarly for the free cantilever end to F, the bending moment at F equals 0. So now if we consider the bending moment at A, so the bending moment at A, and if we just draw it out, you have your point at A, so that's A, that's where we're taking the moment. We have your UD load acting at A, it is acting anti-clockwise, but what we're more concerned about is how the beam bends, where the tension on the beam is. So for this beam, the deflected shape of that section of the beam is going to be something like that. It's going to try and bend it vertically down, so you'll end up with tension on the top and compression in the bottom. Tension on the top, that gives a negative bending moment. So a negative bending moment, that is a hogging moment. So we end up with minus 12 times 1.8 times 0.9, and that equals minus 19.4 kilonewton meters, and as I said earlier on, that is a hogging moment. So it's going to give tension on the top. So if you recall, we draw our bending moment diagram on the tension side. So at that particular point, we are going to have our bending moment diagram drawn on top of the beam. And then if we move along, we go to point D. So the bending moment at D equals, and again, if we consider our loads individually, there we have point D, we have our UD load, and we're also going to have VA. So that's VA, that's the UD load. The UD load is acting anti-clockwise, VA is acting clockwise. So let's consider the UD load first of all. It is acting anti-clockwise. So again, in terms of bending in the beam, it's going to try and bend it down so we have tension in the top, compression in the bottom. If we then think about the vertical reaction at A, that is going to try and bend the beam up. So that's going to act in the opposite direction. That's going to give tension in the bottom and compression in the top. So if we now consider the bending moment at D, starting with the UD load, that's causing tension in the top, so it's going to be negative, so minus 12 times 4 times 2. So that's the magnitude of the load times the length over which it acts times its lever arm, and then going the opposite direction, causing tension in the bottom, so it's positive bending, plus the vertical reaction of 54 times its lever arm 2.2, and that is going to give you a value of 22.8, so it's positive 22.8 kilonewtons, and that is going to be a sagging moment. So that's the bending moment at D. We can now go on and do the bending moment at E. Again, carrying on exactly the same principle, we have minus 12 times 4 times the lever arm of 4.4 meters. So that's for the 12 kilonewton load, because it is causing tension in the top and compression in the bottom of the beam. Now we'll consider the 8 kilonewton load acting about E. It is causing tension in the top, compression in the bottom, so again it is negative, and that's going to be 8 times 2.4 times the lever arm, which is 1.2 meters. That takes care of the UD loads, and the only other load or action we need to consider is the vertical reaction at A. That's going to cause tension in the bottom, compression in the top, so that becomes positive, plus 54 times 4.6, and that is going to equal 14.2 kilonewtons. So that is positive 14.2 kilonewton meters. My apologies, that should have been kilonewton meters for D, not kilonewtons. Bending moments are kilonewton meters, not kilonewtons. And again, at E we have a positive moment, so it's a sagging moment. It's going to cause the beam to sag. Now if we work from the other end of the beam, so we're going to work from the right hand end towards B, so we're going to take moments about B, so the bending moment at B, and we only have one load acting, that's the 18 kilonewtons to the end of the cantilever. That is acting in a clockwise direction, so we have B, that's the point B, we have your cantilever with the point load on the end. That is acting in a clockwise direction. It is causing the beam to bend, to sag downwards. So we have tension in the top, compression in the bottom. Tension in the top, that gives us a hogging moment. So tension in the top gives a hogging moment, and that is negative bending. So it's minus 18 times 3.75, and that equals minus 67.5 kilonewton meters. And as I say, that is a negative bending moment, so it's a hogging moment. It's a hogging moment over the top of the support. And if we want to check that, we could also take the bending moment at B, but we could take it with relation to A. We have minus 12 times 4, that's the magnitude of the load, times the distance over which it acts, times 6.2. So that's from the centroid of the UD load to the vertical reaction at B. That's the first UD load. Now minus 8 times 4.2 times 2.1, again taking moments about B, minus 25 times 1.8. That takes care of all the loads that are causing negative bending, so they're all causing tension on the top, and then we're going to take account of the vertical reaction at A. That is causing tension on the bottom, so it's positive bending, so it's plus, and that's 54 times 6.4, and all of that, if you solve it, ends up with a bending moment at B of minus 67.5 kilonewton meters. So as you see, it makes absolutely no difference which way you work from, as long as you consider either sagging or hogging moments. So you consider sagging moments give positive bending, hogging moments give negative bending. As long as you get that right, then as I say, it makes no difference which end you work from when you're calculating the bending moments at any particular point. Now we've calculated all the values of the bending moment at the particular points, the last piece would be to add the bending moment diagram. And as you can see, I have a bending moment diagram I plotted earlier on, and then to that I would add the magnitude of the bending moment at the different points. So if we just have a look at the plotted bending moment diagram, we know that at the free ends it was 0. That's what we assumed earlier on. And at A, we calculated the bending moment to be 19.4 kilonewton meters. And as I said earlier on, it was a hogging moment. So it was negative bending, giving tension on top of the beam. So we draw the bending moment on the tension side. And then if we have a look at B, again, we know it was a negative moment that gave 67.5 kilonewtons at the support at B. So our supports, we had A here, and B would have been at this point here. Those were the two supports. And then looking at the bending moment diagram, I was talking earlier on about a maximum bending moment. So we have a maximum bending moment approximately midway between A and B, and we calculated that distance. If you recall, if I scroll back up, we calculated that distance Lx to be 2.96 meters from A. So we have a bending moment at a distance of 2.96 meters. That is the maximum bending moment, and we can calculate the value of that. So if we consider the bending moments about this point, and considering the 12 kilonewton UD load first, That is going to give tension on the top, so it's a negative bending moment. So we get minus 12 times 4 times its lever arm, 2.75 meters. Again, we're taking it about the point where the bending moment is a maximum. Then if we consider the second UD load, the 8 kilonewtons per meter, again, that is negative. So it gives minus 8 times 0.75 times its lever arm, 0.75 over 2. And the last load to consider, or the last action I should say, is the vertical action at A. That's giving tension on the bottom, so it's positive bending, so it's plus, that's 54 times 2.96, that's our dimension Lx, and that gives a bending moment at the position of 0 shear of 25.6 kilonewton meters. It is positive, so therefore it is a sagging moment. So at this point here we've got 25.6 kilonewton meters of sagging moment. Again, I've marked that as kilonewtons. It should be kilonewton meters for bending moments. Right, the last part of this particular problem is to calculate the positions of the points of contraflexure. Now, the positions of points of contraflexure, they occur where the bending in the beam to the top or the bottom flanges changes senses. So where it goes from tension to compression, or vice versa, compression to tension. At that point you get a 0 bending moment. So at this point here and this point here we have 0 bending. And we know where that point occurs roughly, because at A we have a negative bending moment, so we got minus 19.4, so we have a hogging moment at A, and at point D, somewhere down here at the end of the UD load, we have a positive bending moment. So somewhere within the 12 kilonewton load we have our point of contraflexure, and likewise at the other end it's somewhere between B and E. Again, because at point E, somewhere down here, we had a magnitude of bending moment of 14.2 kilonewtons. That goes to 16.7, so it changes from tension to compression, or vice versa. Because of that change, you get a point of contraflexure where it's 0, somewhere between those 2 points. So somewhere between the application of the point load and support B. So if we know that, what we want to calculate is the distance from a known point, so we'll take it from A and we'll call that y1, and we will want to calculate a distance from B, as I say, from a known point, so we'll call that y2. That will give us our 2 points of contraflexure. And to do this, you need to formulate a quadratic expression for each. And from that, you can then solve the quadratic to give you the dimensions y1 and y2. Okay, for our 2 points of contraflexure. So for POC1, point of contraflexure 1. So POC1. As I said earlier on, we have to formulate a quadratic by taking moments about the point of contraflexure. So we'll consider first of all the UD load. So we have minus 12 times 1.8, that's the distance over which the load acts between the free end of the cantilever and the support at A, plus our unknown y. That gives the magnitude of the load, and then that is multiplied by the lever arm, which is the 1.8 meters plus y, and all of that is over 2. So that's your lever arm. And the second part of it, we have a reaction at B, and that is going the opposite direction, so it's plus. It's positive because it's causing tension on the bottom. Again, we're taking moments about at the point of contraflexure. Apply the vertical reaction, that causes tension on the bottom, so it's a positive moment. And the magnitude of VA is 54 kilonewtons. And again, that is times the lever arm Y, and then we can set that to equal 0. And if you expand that out, we end up with minus 21.6 minus 12y times 0.9 plus 0.5y plus 54y equals 0. And then again, if we expand the brackets out from there, we end up with minus 19.44 minus 10.8y minus 10.8y minus 6y squared plus 54y, and simplify that to turn it into a quadratic, gives minus 6y squared plus 32.4y minus 19.44 equals 0. And if you solve that using the quadratic formula, you'll get two values of y. One isn't relevant, it's way beyond the beam span, so you end up with only one that makes any sense at all, so y equals 0.688 meters. So that's the first one, that's y1, so we'll call that y1. And for point of contraflexure number 2, so POC 2, again, we're going to take moments about the point of contraflexure. And in this instance, we have the 18 kilonewton load. It is causing negative bending. If we take moments about the point of contraflexure, the 18 kilonewton load causes negative bending because it's causing tension in the top of the beam. So we end up with minus 18 times its lever arm, 3.75 plus y, and then we have a bit of UD load. So we have, again, that's acting clockwise. It is causing tension in the top, so it's negative bending, so minus 8 times y over 2. And the last bit of this one, again, we have the point load at B. That is going anti-clockwise, causing positive bending, so it's plus 70.6 times y. All of that equals 0. If we expand it all out, we end up with minus 67.5 minus 18y minus 4y squared plus 70.6y equals 0. And then if we simplify that to turn it into a quadratic, we end up with minus 4y squared plus 52.6y minus 67.5 equals 0. Then again, using the quadratic formula, we end up with a value for y2 equals 1.44 meters. I hope you have found this video useful. If you have any comments or suggestions, please do send me an email at the address shown on screen. Thank you for watching.